Okay. Everybody should have gotten an email for the course evaluations. Did you get an email? Okay. I'll talk a little bit on Friday about incentives for filling that out. And if you've had your resume done, they'll send me an email. But if you didn't, then the resume is going to go on next semester's sort of extra quiz things. So everybody's going to get credit for it this semester, and then next semester, if you've got it done, great. If not, then next semester you'll go ahead. That'll be one of the things to do, because there's no way they're getting the webs. They'll have the Canvas site up hopefully by the beginning of next semester, they claim. So okay. I thought I did.
Yeah.
I thought I did. If not, I'll do it right after class. In terms of seeing the correct answer, I may not have done that. I'll do that right after class. Okay, the AntiMarkovnikov Addition of HBr. So if we're going to take an alkene and we're going to add HBr and peroxide to it, that's going to change the stereochemistry, or it's going to change the regiochemistry of the reaction. So we know that we're going to be adding H and a Br. We know we're going to be adding AntiMarkovnikov. And then the question is, what's the stereochemistry of this reaction going to be? So in essence, what we're doing is we're adding a Br atom to the double bond. So if I imagine that I'm splitting up the double bond into two, basically giving those two carbons unpaired electrons, and then I'm pairing up the bottom carbon's unpaired electron with the bromine's unpaired electron, I'll be adding the bromine to the carbon that has the most hydrogens, which is the AntiMarkovnikov addition. The reason I'm doing that is because that will leave the most stable radical, which is the tertiary radical in this case. So the bromine adding then gets me a tertiary radical, and so then when that reacts with another HBr, and I'm using half arrows here because the half arrow indicates the movement of one electron. Then that radical pulls the hydrogen off of HBr and then forms the AntiMarkovnikov product, where the H has now added to the carbon with the least number of hydrogens and the bromine to the other one. So that's where we come up with this AntiMarkovnikov addition. I changed the mechanism. So the question is, what about the stereoselectivity? Do the hydrogen and bromine add cis, trans, or 50-50? And in order to answer that question, we need to look at the structure of a radical. And we also need to look at the structure of a carbocation. So if you remember, carbocations are sp2 hybridized. They have an unhybridized p. The other bonds are trigonal planar. And because it's a positive charge, the orbital is empty. So when we had our nucleophile, then our nucleophile would add 50% from the top, 50% from the bottom. There was nothing keeping it from adding or making it add to one side preferentially over the other. So the structure of a radical is very similar, except now you have that unpaired electron in that p orbital. And so because the radical spends 50% of its time in the upper and lower lobes, it's going to remove the HBr 50% of the time from the upper lobe and 50% of the time from the lower lobe. Which basically means that there is no selectivity. It's adding 50-50 cis and trans. Okay. So the third part here is going to be adding 50-50 cis and trans. So the only thing different is the anti-Markovnikov addition versus the Markovnikov addition. So that's the essence of anti-Markovnikov addition of HBr and then the peroxide. The peroxide changes the mechanism from being a carbocation to being a radical. And what that really affects is the regioselectivity, not the stereoselectivity. So in the reaction that we just did with this product on the right being the major product, is the reaction regioselective? In other words, forming this as the major product, is the reaction regioselective? Yes. Because adding Markovnikov and anti-Markovnikov gives two different products. Did it select one? Yes, the anti. So this reaction is regioselective. Is it stereoselective? But I created two chiral centers. I created two chiral centers, but the reaction added 50-50. If I created two chiral centers and it added 100% cis or 100% trans, then it would be stereoselective. Okay. When you look at the flow chart that I had drawn up, it says the first thing is, does the reaction go through a carbocation or a C dot intermediate? The C dot is the radical. So if it either goes through either one of those, it is not stereoselective. Okay. So given this and the mercuration, demercuration from yesterday, we've got a couple different reactions to add to the chart. We basically have three more. Because mercuration with water, mercuration with alcohol, and then anti-Markovnikov addition of HBr. So that table can be extended 3 more rows. It's locked. Thanks. How did I lock it? Okay. So that's where that one comes into play. Any questions? So we have to remember HBr, anti-Markovnikov addition, 50-50. Now, we're going to talk more about free radical mechanisms next semester. But the problem with a free radical mechanism is that when you take one radical or one atom, like a bromine atom, in this last step, for instance, this radical reacting with HBr generated another bromine dot. So radicals, when a radical adds, it tends to produce another radical as a product, and so the process just continues. So one of the things that in biochemistry that we have to worry about is, well, in biochemistry and food chemistry, is that we have no choice but to take into our systems oxygen gas, right? We don't take in oxygen, we die. And so oxygen has a free radical component to it. This is the paramagnetic form of oxygen. So when this form of oxygen gets into our system, it can act like a free radical. And so it can actually begin a cascade of removing hydrogens. And then if certain molecules, like we don't want our DNA, or we don't want enzymes, or we don't want proteins to be reacted to have hydrogens removed, because then that can lead to mutations, which can either be good or bad. So we have to somehow have antioxidants in our systems. And there's a couple of different ones. I'll show you the one for food that happens in food. Because food, it's the same thing. Oxygen is what leads to food spoilage. And it can react then in this free radical mechanism as well. So there are compounds, like this is one where we have a terse butyl group and a couple of methyl groups on a benzene ring. This is called a phenol. Phenols are when the OH is attached to the benzene ring. So these types of antioxidants stop the cascading reactions. And they do so because if this radical was to pull off the hydrogen of the phenol, we would make that oxygen would have an unpaired electron. But then that unpaired electron could actually be stabilized by drawing a number of resonance structures. So for instance, I could split this double bond and pair it up with the unpaired electron. So that it would form that resonance structure. And then I could continue this process around to the other two double bonds. And so this is a standard preservative that you would find like in food. If you look at a food wrapper, if you see BHT or BHA, those are phenolic type preservatives. They're going to react with any oxygen present, and they're going to form a stable radical that is not going to have any real desire to go around and dehydrogenate something else. So you form stable radicals, and then that kind of kills the process, because you don't want radical after radical after radical forming. So in our systems, we don't have necessarily these kinds of antioxidants, but we have things like vitamin C. Well, vitamin C is questionable depending on its condition. It may or may not be an antioxidant, but things like beta carotene from lab that have the long series of alternating double and single bonds can do this. The vitamin E, if you've heard of that, that's an antioxidant. So all of these produce a stable radical that doesn't continue the process. So that's how antioxidants work, is that they stop the cascading reactions. Okay. So we'll talk more about this next semester, because we'll talk about having a radical in the what's called allylic position to the double bond. And that's a very stable radical, but it also has those resonance structures. All right, so that's HBr, AntiMarkovnikov with peroxide. All right. Everybody kind of okay with that? So let's do the final reaction that will go on the chart of adding things to double bonds. And that is what's called cis hydroxylation. So in cis hydroxylation, I'm going to add two OHs to the double bond. Is there a need for Markovnikov or anti-Markovnikov? No, because it's a symmetrical reagent. And this is going to add 100% cis. And the mechanism that I'm going to show you again is not something that I'd ask you to repeat, but it will show you where the 100% cis comes from. All right, so I'm going to take a double bond, and I'm going to add to it one of two reagents. The first one will be KMNO4. Bless you. So now, let's go back and review our shapes of intermediates. So a triangular intermediate gives you what? 100% trans. A square, cis. Right? So then this is going to be a pentagon. A 5-membered ring. So a 5-membered ring will also be cis. And those two OHs are going to be added basically at the same time. So a 5-membered ring isn't big enough to have one oxygen add from below and one add from above. Five-membered ring's not big enough. It has to be probably closer to 7. So this is going to be cis. So KMNO4, you've used KMNO4 in like general chemistry. It's purple. You've done titrations with it. KMNO4 is an oxidizer. In organic, that means it gives oxygen to molecules. And in general chemistry, it basically undergoes reduction itself. So we can actually see that in this reaction. So if I change, I'm just going to rewrite the double bond here. So potassium with the plus charge, permanganate with the minus. I'm going to ignore the potassium, and I'm just going to write the structure of permanganate. So there's the structure of the permanganate. And so what happens in order to form this 5-membered ring and to add the two oxygens to the same side of the double bond, I'm going to take this pair of electrons and give it to the carbon to form that OC bond. I'm going to break the carbon-carbon bond, and I'm going to use that to bond to the other oxygen. Then the MnO double bond is going to go to the manganese. So this is the way the arrows would go. Now the first thing is the manganese is gaining electrons. So again, I use the Leo, the lion goes grr, lose electrons, oxidation, gain electrons, reduction. So what you can see is manganese is undergoing reduction. From general chemistry, anything that undergoes reduction does what to the other species? It oxidizes it.
You said we won't use like oxidation and reduction in these terms in this class.
We normally don't because it's hard to see, but this is one of the cases where it is easily seen. So usually with a metal, you can kind of see the oxidation or the reduction. But normally we don't, unless it's really easy to see, which is this case. So manganese is undergoing reduction. The double bond is gaining oxygen, so it's undergoing oxidation. So the 5-membered ring then looks like this. And that 5-membered ring is not big enough to add those two oxygens trans. So those two oxygens must be added cis. So then I actually forgot a reagent. It's KMNO4 and hydroxide. So when you react a double bond with KMNO4 and hydroxide, what happens then is the hydroxide and the water come in and they strip off the manganese part to then give me the cis addition of the two OHs. And that's an inorganic mechanism, so we're not going to really talk about that. The only reason, again, I'm showing you this mechanism is so you can kind of associate this 5-membered transition state intermediate with the idea that it's adding cis. Okay. Now, KMNO4 and hydroxide adds two OHs cis. On Friday, we're going to talk about KMNO4 and acid, which does something completely different. So there's going to be two KMNO4 reactions. But this one adds two OHs cis.
Wait, where does the second OH come?
There's these two oxygens become OHs from the reaction from the manganese being pulled off. I mean, you can imagine the manganese being pulled off and those being two O minuses that then immediately like deprotonate water. Okay. So that's one reagent. The problem with the permanganate, and it's not really a problem, permanganate's dirt cheap. I mean, you can buy tons of permanganate. It's not that expensive. It is an oxidizer. So, for instance, like if you have a fish tank and it gets cloudy, then you go to the fish store and you buy like water clearer upper. It's basically potassium permanganate. You put a couple drops in, and the permanganate reacts with all the organic stuff that's clouding up your tank, adds oxygens to them, makes them water soluble. Tank goes clear. Too much permanganate kills fish, but just a little bit will oxidize all of the fish wastes and other things that are making your tank cloudy. So it's really inexpensive and actually readily available.
What's the manganese in the final product?
I don't know. It's some manganese oxide stuff.
So manganese won't even be in the final?
No. We're only interested in this. We're only interested in the final organic product. So the manganese it probably undergoes another oxidation reaction or something. So we're not concerned about its final fate. So when you do potassium permanganate with an alkene, you've got to use it 1-to-1, 1 mole to 1 mole, which isn't bad because it's cheap. The other reagent that you can do this reaction with is called OSO4. And this is called osmium tetroxide. So osmium tetroxide is an alternative to this reaction. And it pretty much does the same thing. In this case, the double bond, the pair of electrons from the double bond goes to form the CO bond, the CC bond breaks, and that pair of electrons goes to form the carbon-oxygen bond. So you end up with the exact same type of transition state or intermediate compound. You end up with that osmium compound. Again, 5-membered ring, oxygens have to add cis. Now, the problem here with the osmium tetroxide is that it's expensive. And so it's too expensive to use on a 1-to-1 mole ratio. So what people do here is they react with osmium tetroxide and hydrogen peroxide. So what happens is that the hydrogen peroxide reacts with that species, removes the osmium. We form our cis hydroxylated product, and then it regenerates the osmium tetroxide. The hydrogen peroxide regenerates the osmium tetroxide, so now it can go back and react again. So therefore, I only need a little tiny bit of osmium. I can use a lot of peroxide, so I can just keep catalytically regenerating the osmium so that it makes the reaction economically feasible. Because I'm just using a tiny bit of osmium. And I'm using hydrogen peroxide that isn't really a environmentally bad reagent. Hydrogen peroxide is pretty good. Okay. So both of those reagents would work. Everybody kind of with me? All right, so we go to this reaction, and we react it with, let's react it with OSO4, H2O2. And so now I have to write my product. I have my CH3 attached to the top carbon. What am I adding? I'm adding two OHs. How am I adding them? 100% cis. So that means they both get a bold wedge or dashed wedge, and then the methyl group gets the opposite wedge. So there's my major product.
So these ones you are only asking, or you only could ask major product, not the mechanism?
Right. I'm showing you the mechanism to help. You know, people have their own systems, right? So, you know, hopefully you've seen over the course of the semester that I try and explain things different ways, not to confuse you, but so that one of those ways you can sort of grasp onto. Maybe it works, maybe it doesn't, but that's why you have to go through with this. You have to go through and kind of figure out your system to learn this. Because I can't impose the system on you. I mean, I could, but it's not going to be effective for everybody.
Can we do the regio and stereoselective?
That was going to be my next question. So regio-selective? No? Why not? Adding a symmetrical reagent. So this one is not regio. Stereo? Let's boil the flowchart down to two questions. First question, did I add the two groups 100% cis or 100% trans? Yes. Did I make a product with two chiral centers? Yes. So if the answer to those two questions is yes, then this is stereoselective. You can still go down through the chart, but ultimately that's what stereoselectivity is. We made two chiral centers and we added those two groups 100% either cis or trans.
Are we going to do regio specific this semester?
We're going to do that next.
Oh, okay.
The next reaction is going to be regio specific.
Okay.
Or sorry, stereo specific. There is no regio specific.
Oh, it's stereo specific. Okay.
Stereo specific, yeah. We've actually already done it once. So give me a few minutes. Okay, so that's the last of the addition reactions. Two OHs, neither Markovnikov or AntiMarkovnikov, 100% cis. Right. Okay, so we have two more sets of reactions to talk about. cleavage, which will happen on Friday. And the next one is compounds called epoxides. Epoxides or oxiranes. Epoxide is kind of a common name for these molecules. Oxiranes is more the IUPAC formal name. So what is an epoxide? An epoxide is when you have a three-membered ring with an oxygen at the top. And epoxides can either be cis or trans because they basically have bold groups and dash groups. So two groups that are on bold are cis, one on bold, one on dash is trans. So this epoxide is an intermediate compound. We can make it, we can put it in a bottle, but it's not necessarily useful by itself. It's useful in the reactions that we can do with it. So first question is, how do you make it, and then what do you do with it? So how do you make this? Well, we go back to our previous friend molecule that we made, which is called a bromohydrin, right? We made bromohydrins by reacting bromine and water with the double bond. The bromine and the OH always added 100% trans because it went through the triangular intermediate. So if we make a bromohydrin, it's not really that useful by itself, but what is useful is if I react that now with hydroxide. Because what will happen is the hydroxide will come down and it'll deprotonate the OH. When it deprotonates the OH, it forms an alkoxide, the O-. Now this O- is going to be a good nucleophile, so it's now perfectly set up to backside attack that carbon, kick the bromine off, and we make our epoxide. Okay, so that's one of the ways to make an epoxide, is to first of all make a bromohydrin and then take that bromohydrin and basically deprotonate it with hydroxide. Second way to make an epoxide is a one-step process. And that is to take our double bond, and I'm going to put in bold and dashed wedges here for a moment. So we're going to take a double bond and we're going to add to that what's called a peroxy acid. And I'm just going to use generic peroxy acids. We'll get a little specific later on. So this per, what does this per term mean in chemistry? Well, water is H2O, or HOH. Hydrogen, you could call water hydrogen oxide. It would normally be called hydrogen monoxide. And if you want to laugh, you can look up on the internet how dangerous hydrogen monoxide is. It could kill you. Could if you drowned in it, right? So there are all the dangers of hydrogen monoxide. But what's H2O2 or HOOH? It's hydrogen peroxide. So the per term just means I've added an oxygen. So when I have a carboxylic acid and I add an extra oxygen to it, it becomes a peroxy acid. So this is a peroxy acid, and what happens is we're not going to go into the mechanism of this, but if you can imagine you have the double bond, what's going to happen is the oxygen is going to plop right on top of the double bond and form both of the bonds at exactly the same time. So when we make our peroxy, or when we make our epoxide, what's going to happen is that the stereochemistry, let's say I had an R group here, an R group here, an H and an H there. So if I had a cis alkene, I will make a cis epoxide. So the stereochemistry of the alkene is preserved in the epoxide product. And that is where the stereo-specific comes into play. This is an example of a reaction that is stereo-specific. Now, stereo-specific was introduced in the book a while back, and I said, let's wait until we get to another reaction that makes a little more sense. This is the reaction. So, in order to understand stereo-specific definition, you have to understand the definition of what is selective. So when we talk about reactions being selective, we're focusing on the products, right? We're saying you have the possibility to make more than one product. Their relationship tells you whether it's regio or stereo, but you have to select one of those two products. That's what selective means. Specific, you focus more on the reactants. So a stereo-specific reaction is one where if I change the stereochemistry of the reactants, I then get a different product. So in other words, I start with cis alkene, I get cis epoxide. I change to a trans alkene, what kind of epoxide do I make? A trans one. So when changing the stereochemistry of the reactant then causes the stereochemistry of the product to change. So that's stereospecificity. Josh?
If, for instance, the alkene has one R group is trans and one of them's larger than the other one, is going to select which side?
No, because what's happening is the epoxide's sitting right on top of it. So whatever the configuration was here, you're basically erasing the double bond, putting the oxygen right on top of it. So what there is not the ability to do is to rotate. So right now, this is not a happy alkene because it's got two alkyl groups cis. But it doesn't matter in the final product, I'm just going to have a cis epoxide because it will not rotate. The oxygen comes in and plops it right on there. No change in stereochemistry. That doesn't mean, though, that a stereospecific reaction can't change its stereochemistry. Because this is our example of a stereospecific reaction of an alkene. But we saw stereospecificity, we didn't call it this, but we did see stereospecificity when we talked about an SN2 reaction. Right? Because what happens if I take an R molecule and I do an SN2? What do I get on the other side? Get an S. What if I change the stereochemistry of the reactant to S? What do I get? R. That's stereospecific. That's a stereospecific reaction. Okay? So, stereospecific is, well, I mean, it is very specific. It's a very specific kind of reaction. When you first see this, you might think, you know, I'm not going to tell you what you might think. Because then somebody will think that. And then they'll say, but you said that. Well, I said that was wrong, but okay. What I was going to relate it to was the idea that, remember, selective is all the way from 5149 all the way up to 100. Right? In terms of selectivity. It's all selective. Even if it's 100 to 0. Sometimes you might think this term is 100 0, but it's not. It's a completely different reaction. Okay, so we make epoxides. Great, we can do that. We can do that one of two ways. So what do we do with the epoxide when we're done with it? We react it. We open it up. How do we do that? Pure 100% review. Okay, I'm not going to say anything that isn't already been said more than once. So let's see how well you've been paying attention. Oh, not just today, for the last 2 weeks or so. Okay, so one of the ways that I can open up this epoxide is to react it with acid. What's going to happen? Kevin?
The hydrogen's going. It should attach to the C with the two H's.
Not the H+. You're getting ahead. That's the next thing I'm going to do is I'm going to react it with one of those two carbons. Well, what's the H+ do?
Protonates the oxygen.
Protonate the oxygen. How many times have I said that? A lot. So what we're going to find is, just now and in the future, is whenever we have a molecule with an oxygen in it, we add H+ to it, we're going to protonate the oxygen. Or we could protonate the nitrogen with other molecules, but we're going to protonate the oxygen. Right? Sometimes repetition's good. It will be if I start asking you what's going to happen. So you see this? You can make yourself look good and automatically say, protonate the oxygen. That's what we're doing. Great. Again, that was not new. All right, so I do that. I now have that species with the plus charge on the oxygen. I'm having a sense of deja vu. That means I've already seen this in French. Anybody else having a sense of deja vu? Anybody else having a sense that they should have a sense of deja vu?
A little bit.
Should be more than a little bit. Because we did this a long time ago. Monday. So I'm looking at a triangle with a plus charge on the top.
Because it has a positive charge, it's going to be attracted to whichever carbon has the highest delta negative charge, which would be the left one without looking at it.
Nah, you're close. You're getting some of the elements. Okay, we don't remember exactly what it is. Nobody wants to throw out a name. David?
Couldn't be, but gonna move the carbon on the right. That
You're getting way ahead of me. You're getting way ahead. And I haven't reacted it with anything yet, so I don't know what carbon it's going to add to. Actually, I do, but
It's kind of like the intermediate for the mercurization.
it looks like a mercurium ion for Monday. Right? When the mercury plus was sitting on the triangle. Oh, wait, I'm remembering something else. That kind of looked like what before it? When there was something on top with a plus charge. Bromonium ion. Right? The mercurium ion on Monday looked like the bromonium ion from the past. Well, I know it was before Thanksgiving. That was a long time ago. Just wait until next semester comes, and it's like, oh, I haven't looked at organic chemistry for like a month. You want to try and, put corks in your ears, whatever, keep the stuff in there. Whatever you end up with at the end of next week, try and keep as much in there as possible. for next semester. And maybe even add a little bit more. But this looks like a bromonium ion. It looks like a mercurium ion. So oxygen's not happy at the plus +1 charge, right? So what does it do? It shares that positive charge with those two carbons, making them slightly positive. Actually, if the oxygen has its complete way, it's going to get rid of all the positive charge to those two carbons and make them share it. So then, let's say I add H plus H2O to my epoxide. Now my water is going to add, first of all, relative to this OH group, that water is going to add cis or trans. Trans, right? Triangle, trans. So it's going to add from underneath. Is it going to add to carbon A or is it going to add to carbon B? Well, let's just talk generically. Let's psychically go back to Monday. What group is the water going, what carbon is the water going to add to? The one with the most substitution, because that one has the most delta positive charge.
So this looks like bromanium ion, which added Markovnikov, but we're adding an
No. Markovnikov and AntiMarkovnikov actually don't apply here. Maybe similar, but they don't apply here. But the rule is pretty much the same. Remember, the bromonium ion was taking the place of the hydrogen so that it would slide over to the carbon with the most hydrogens.
Oh, but this we're not adding. But this we're actually adding an H, and that's why.
Right. The OH is going to slide either right or left. The water is going to add to the carbon that's most substituted, the carbon with the most delta positive charge, which is that one. So that then we break the OH bond and the OH slides over, so that at the end of the reaction, what we end up with is we end up with an oxonium ion and then what's going to happen to that oxonium ion? It's going to lose H plus to give me two OHs. So in essence, in this reaction, here's what I've done. I've added two OHs with what kind of stereochemistry? Trans. This is the perfect time to talk about adding two OHs trans, because what did I just do 20 minutes ago? I added two OHs cis. So I can't add two OHs trans in one step. But if I turn the double bond into an epoxide and then add H plus H2O, I can now add the two OHs trans. So I have this ability to make both kinds of dialcohols. Okay. So we'll talk about some of the other reactions that I could do, because what if I added H plus Br minus? What if I added H plus alcohol? What if I didn't have H plus to begin with? What if I just reacted this with Br minus? And then we'll do cleavage, and then we're done. Okay, so that's what we're going to do on Friday.
And you said you're gonna fix top hat.
I'll fix top hat right now.
Wait, so we're not having any final review?
The final, there's a big set of problems, and that's available along with the answers right now. So I wasn't going to use Friday for a final review because it's more than one day's worth of review. If you have questions, bring them and we'll finish this up and you can ask away, but